Hello there, this is another lesson on the SUVAT equations, and you've probably seen the SUVAT equations already. We're going to look particularly today at using the SUVAT equations in situations where the acceleration is caused by gravity. Things are going to fall to the floor, as this couple of skydivers are trying to show you. And when things fall to the floor, admittedly without a parachute attached to their back, they do so at a set rate of acceleration, and we'll have a look at that in a bit. Now, first of all, I suppose the first thing I want to do with you is to see that you know what the SUVAT equations are. Now, I've said to here, write down the first five, or the five SUVAT equations without looking. So I'm going to pause it. I want you to try to remember what they are, and you should know what these are. So I'm going to pause the video. I want you to do the same, and then I'll put the answers up. I'm hoping now you have remembered it and you've written them down. And you can't underestimate the importance of learning these off by heart. But here are my answers anyway. So you have v equals u plus at. You have s equals a half u plus v times by t. You have s equals ut plus half at squared. So there are two different s equations, if you like. We get a third one which you don't see in physics. So this is why this one that often gets missed by people who are very good scientists. S equals vt minus a half at squared. So now we've got three s equations. And the last one, v squared equals u squared plus 2as. And again, we've got two that start with v. And the advantage is, of course, that each one has its merits depending on which letters you know or don't know. Anyway, so Galileo, some 400 odd years ago, was the first mathematician to be publicly famous, if you like, for knowing that objects fall at the same constant rate, and that rate is called the acceleration. And most people at the time, and probably still now, don't believe that. They think that heavy objects would fall quicker, but they don't. They just fall at the same rate. Now, obviously, there's a bit of slowing down, certainly, of some objects due to their friction based on some objects fall slightly different rates, but broadly they fall at the same rate. And Galileo was the first person to prove this and show this. And he and others have since found that the gravitational constant, constant acceleration, is 9.8 meters per second. Now, I remember doing this in physics and being told it was 9.81, and some other people told me it was 9.82. But in maths, you don't care. 9.8 is good enough. And if you use 9.81 or 9.82, you'd probably lose marks because you won't get the same right answer, if you like, the answer that they're expecting. So use 9.8 in maths. Example one, a stone is thrown downwards with a speed of 5. Okay, then, so it starts off, and this is the way I think about it. So if it was me, I tend to write SUVAT out like this, SUVAT. And each one of those is going to be possibly something I have. So I know it's thrown down at a speed of 5. So that's my u. It's my initial velocity. From a point 2 meters above the ground, modeling the stone as a particle and ignoring air resistance, right? That means it's falling with a rate of 9.8. Find the velocity when it hits the ground. Well, it said it was 2 meters above the ground, so that's 2. Find its velocity, so I want v. So that's what I want. And so I haven't got my t. That looks to me like v squared equals u squared plus 2as. So over here, I'm going to write v squared equals u squared plus 2as. And put my numbers in. Well, v is what I want. That's lucky because it's on the left-hand side already. It's already the subject of the equation almost. V squared equals u squared, which is 5 squared. Well, I know that's 25. Plus 2 times a, 9.8. Times s, it falls 2 meters as well. So I type that into my calculator. 25 plus 2 times 9.8 times 2 is 64.2. Now, of course, this needs then to be square rooted because this is v squared, 64.2. And v, if I square it, it's got to be 8 point something or other. Let's just do it here on a calculator. 8.01 according to me to 36 figs. Meters per second. So what the answer says it is 8.01. So by pure chance I left that gap for it. So I like that. Example 1 is done. Now this one at a swimming pool, girl steps off from a diving board. So this looks, again, I'm going to write over here, so the SUVAT. So I personally like writing those letters out. And it says, at a swimming pool, a girl steps off from a diving board 4 meters above the surface of the water. So I assume she's going to fall 4 meters. How fast is she moving when her feet hit the water? Well, she steps off, so I suppose that implies that she's got no speed when she steps off. She's literally starting and she's going vroom, thereafter. She's going to drop to the floor. How fast is she moving? That's what I'm after, the V. And again, it's 9.8 as she falls. Again, it's the same equation as last time. I'm going to use V squared equals U squared plus 2AS. Excuse my dodgy pen. So V squared equals, what's my U squared this time? 0. Naught squared is 0 plus 2 times 9.8 times 4. And of course, the 0 I can completely ignore. V squared equals then, it's just 2 times 9.8 times 4, 78.4. And to get my V, I have to square root again. Square root of that answer is 8.85 to 3 sig figs. I think I've got that right. So 8.85 is the answer to the first section. This, I suppose, is A. What's it then say? How long does it take? Oh, right. Now, this is exactly the same, but now I'm going to find this one. So how long does it take to reach the water? So this time, I don't know my V. If I don't know my V, I'm just looking at that. S equals ut plus a half at squared. That's the one. This is why it's useful if you know these off by heart, because then you find the equation a little bit quicker. Do I want S? No, I've got S. S is 4. U, the good thing about this is U is 0, and 0 times anything is 0. So that ut is gone effectively. Plus a half times A times t squared, and it's t that I'm after. So if you work out a half of 9.8, obviously the naught disappears, I get 4.9 t squared. That equals 4. And if you like, t squared therefore is the 4 shared by the 4.9. I'm going to do it on my calculator. 4 divided by 4.9 is 0.816. Now, it's not exact, so don't round it too quickly. Just now use your calculator to find the square root of 0.816. So square root of the right answer is 0.904 to 3 significant figures, and this is seconds. So let's see if my answers agree with that. Answers 8.85 I got, 0.904 seconds. Perfect. So nice little question so far. Let's go and have a look at a third example. Now, when you throw an object, normally, of course, when you throw an object, you throw it at a place, and it goes somewhere else. It goes over there. It goes from your hand, to probably the floor. But we are simplifying this slightly, in as much that we are going to throw a ball, and very often it won't start from the floor. It will go straight up, and miraculously miss you and go straight down again, and it hit the same floor. And so this is what we are looking at now. A ball is thrown vertically upwards and rises to a height of 10 meters above which it was thrown. All right, so it starts off there. I don't know where. All I know is it ends up here, which is 10 meters above itself. Okay, that makes sense. What's it say? So I'm going to just start with SUVAT here. So this is my common technique on all these SUVAT questions. I just write out SUVAT. So I find the speed for which it was thrown. So it's thrown vertically upwards. So the acceleration rate, once I've let go, is minus 9.8. Notice I treat upwards to be positive, downwards to be negative. And if that's the case, as soon as I let go, it's pulling down on it. It's no longer going to be a positive 9.8 because my motion was upwards. So in the last question, we just said A was 9.8, and that's because I dropped it and it went downwards. So you can see here, my motion is downwards and my acceleration is downwards. So I kind of ignore the fact it's downwards and I just pretend it's all positive. But when you get a question like this, where you've got it goes up first, the best way to deal with it is to escape with upward motion is positive, downward motion is negative. And so that's why I've got over here, it's a downward 9.8. That's a subtle difference you've got to get your head around. And it's all come about because I've decided to throw my object upwards first of all. It's thrown vertically upwards and rises to a height of 10 meters. So it will go 10 meters. It's thrown vertically upwards. I'm going to assume it starts at a speed of 0 because it doesn't say it was thrown. Oh, right. No, it's not. We're talking rubbish there. There's the speed with which it was thrown. That's what I want. In fact, that's my question mark. Just goes to show you, sometimes you just have to work out what's going on. So what is the... Oh, I now understand it. Once it's got to 10, its velocity at the top must be very, very temporarily 0. So this is, again, a common thing that we get. We've got this... ball going upwards, and at the very top it's v equals 0. Okay, now I know that. I want to put that there as 0, and my equation again is v squared equals u squared plus 2as. Third time I think I've seen this formula today. So v equals 0 squared, u squared I'm trying to find, plus 2 times minus 9.8 times 10. So if I do that, I think that's 196. I'm just going to check. 2 times 9.8 times 10. Yeah, 196. So 0 equals u squared. But of course it's a negative minus 196, which moves over to the other side. U squared, therefore, is 196. And u, if you square root 196, it's 14. It's one of the reasons this number 9.8 is used so happily, because, ooh, that's a minus 1. That's the minus 1. Or meters per second. It's used so happily because it gets you such nice numbers when you get a question like that. Find its velocity when it has risen 7.5 meters. Oh, right, this is slightly different. So let's just do it again. SUVAT. So it's not going up 10 meters now. So on my picture, it's still moving. So it only goes to about there, 7.5 meters. That's a terrible scale, but you get the idea. So it goes up 7.5 this time, and therefore it's still got a bit of pace. It's still moving upwards. So S this time is 7.5. U I now know is 14. I can just use 14. That's handy. A is still minus 9.8. And what's it say? Find the velocity I want. So it's the same thing. V squared equals U squared plus 2as. And this cricketer throwing the ball here, not him obviously, because he looks as if he's throwing it sideways. But this ball which has been thrown up, I can now write v squared equals u squared, 14 squared, that's 196 again, plus 2 times minus 9.8 times 7.5 ds. So if I just work that out, 14 squared plus 2 times negative 9.8 times 7.5. And I've got an answer of 49. Obviously, someone's planned this in advance, you can see, because now I can square root, and I get 7 meters per second. So, again, let's just check. Ooh, my answer's a bit hidden there. They do vaguely say 14 and 7 there. So I hope you agree with those. So, but at least I now know they're right. Though I could just briefly see them. Example 4. Now this one strikes me as a good time for us to stop. I'll save this example as a class example that we'll go through during the lesson, and that will be a nice way to start. But I hope that makes sense. Remember then we've got these 5 equations. Interesting, I think I only used 2 of them, but depending on how the question is set up, you can be using any one of them. The ones I picked, it seemed always to be v squared equals u squared plus a squared, as I could see. But you could be any of the equations. So I'm going to leave it there. This will be our starting point for the lesson. Thank you very much. All the best.